Hello everyone. In this model, we're going to start with a discussion of the basic building blocks that allow neural networks to deal with images and allow to solve such tasks as image recognition and segmentation, tagging, etc. Namely, we're going to talk about convolutions and pooling. And in the second episode, we're going to turn neural networks inside out, and instead of compressing the high dimensional feature space into a low dimensional, high level class labels, class distributions, we're going to start with a compact representation and random noise and get some feature distribution that can work as an image or work as an some kind of tabular data set. Let's
start with the basic building blocks that is used for working with images using neural networks. So when a human looks at an image, it usually triggers a series of association. Looking at this particular image, we may think about a kid, about a superhero, about times during which the person plays such kind of games, or we can think about the artist that has produced such paintings. And for a computer, if it is a grayscale image, things are much more simpler. So it is a tensor of two dimensions of certain height and certain width that consist of elements that are called pixels, and each pixel represents a brightness in the range from 0 to 255. In case we have a colored image, it is essentially a combination of three individual channels, red, green, and blue, that contribute to the colored image. So in that case, we have a three-dimensional tensor. Every dimension is encoding the height, width, and number of channels. Depending on the library that you're dealing with, a number of channels can go as a last element or as a first element. It is not really important, but you have to know which exactly is the case. So the general idea how you can work with image, you can transform those W times H pixels into features and send those features into a hidden layer and transform using some operations that you learn during gradient descent, and in the end you get predictions of the image belonging to a certain class or object on the image representing certain kind of class. But if you use a regular logistic regression or one hidden layer of represented by matrix W and bias B, and some nonlinear transformation afterwards, is the following. So imagine you have an object inside the image that you want to recognize located at certain part of this image, say bottom right part of this image, and if we have weights that are learned to identify this object in this region, it will be a completely different case from the location of the same object in the different region. So if we have the same face or same kid in the upper left part of this image, we have to learn how to trigger weights in the different region. And for neural networks, those two different cases have to be treated separately, which isn't very practical, because we would have to take care of all possible positions of the object inside such an image. So instead, maybe we can encode these characteristic features that represent the object that we want to recognize by some kind of portable tensor that we can run across our input image that would be able to identify the presence of the object inside the image. So imagine that we have a kind of portable detector that is described by certain weights, and we apply this portable detector to every region inside our image. So we have detector 2 by 2 and image 3 by 3. So it means that we have 4 different positions how we can place our detector inside this image. Right? So it will literally produce 4 different numbers showing whether or not we have image of the kid in specific location. So looking at those 4 numbers, we can see that there is a clear indication and there is a kid located in the bottom left part of this image. And we can come to conclusion that there is an object that we were looking for. So, and here is a mathematical operation that is called convolution that describes the process of iterative applying weights to all pixels at our image. So in case we deal with just one-dimensional vectors, so we have vector of weights and we have vector of input image, and we just compute the dot product of the weights of the sliding window of the same size as the size of the weights. So first we apply it here, then we shift by 1 element, apply here, and shift by 1, and shift by 1, and shift by 1. Okay, so we would have in total 5 different products that would be stored in the output. And we can just write this as a single operation. The two-dimensional case isn't much different. So here is the illustration when we have this weight matrix that we may call a filter or a kernel. So it is just a matrix, in this case 3 by 3, with certain weights that are supposed to encode features or objects that we want to find into the input object, into the input image. And we run this filter through all possible locations of the original image. And we compute this dot product for every position and store this dot product into the two-dimensional matrix that correspond to all possible locations of the filter inside original image. And you see that we can find a pattern that is similar to the one encoded inside the filter in the original image. So we see a clear indication that is something that is similar to the cross sitting in this region. So, and here is the process, how this product is computed iteratively. So you start with image 5 by 5 and your filter is 1, 0, 1, 0, 1, 0, 1, 0, 1. So it is decoded by those red numbers inside the yellow square. And for every dot product, you store the output inside the convolved feature map. So original feature map or image is represented by green pixels, green elements, and the convolved feature map is depicted by the red ones. So the intuition behind this is computation of the likeliness of presence of the object that we want to find in the original image. And there are different kinds of convolution kernels that may serve specific purposes. So this particular example is good for detecting edges. And for example, in Photoshop, you can find a lot of different filters or kernels that help to sharpen an image or soften the image or produce some specific transformation. There are certain tricks that you have to keep in mind or aware of when dealing with convolutions. So we talk about padding, we talk about stride and dilation. So padding is just the case when we want to have size of the input image and the output image to be exactly the same. Since we reduce size of the output by dimensions of the kernel by size of the kernel -1. So if originally we had a 5 by 5, the output will be, if we have a kernel 3 by 3, the output will be 3 by 3 because we can place kernel 3 by 3 in 3 different positions along one axis in 5 by 5. And if we want to go from 5 by 5 to 5 by 5, then we would have to add a special external pixels, virtual pixels, and this procedure is called padding. So you can pad with zeros, or you can replicate what is present at the edge pixels, or you can have circular padding, which takes pixel from the other side of the image, etc. And then those are parameters of the PyTorch model that represents convolution operations. And another approach that can help dealing with convolutions is called striding. So instead of applying our kernel to every possible position, we can move along every axis with certain step, which is called stride. As you see at the illustration here, we move by 2 pixels, and it is effectively reduces size of the output feature map. Also, one of the tricks how to reduce the size is called dilated convolution. So it's just applying the convolution not to consecutive pixels, but pixels that are sitting at certain distance. So as you see, dilation, here is no dilation, here is 1 pixel gap, and here is a 3 pixel gap between individual elements. So it effectively allows you to process larger input images and save some space for the weights that are going to be learned by the network. So let's have a look at the demo how the convolution works. So here is the image of the camera from my iPad, and I can play with different kernels. So originally it was edges, then I can switch to blur or to sharpen, and on the bottom right you see the kernel itself that is applied to the original image. And you can introduce striding that effectively reduces the size of the output feature map. And you can change it back, and you see that there is a 1 pixel width, 1 pixel margin that is introduced because the output feature is smaller than the original one. So if I add padding and I switch to another kernel, you see that the image has extended by this particular pixel. not as much as I expected. I wonder why is it so. Let me refresh this page. Well, at least you see that there are some pixels that are occupied there. I'm not sure it works 100% correctly, but I hope you get the idea. So we with padding equal to 1, we add 1 more pixels at the edge of the original image, and it computes the dot product on these images and those pixels as well. So for blur, it seems to be working more obviously than for other kind of filters. So getting back to the presentation, so here is the mathematical representation of the operation of the convolutional operation pi performed by PyTorch. And it is important to keep in mind that during the gradient descent, what the optimization does, it adjusts the weights of the kernels inside convolutional layers that we have specified in our network. So we explicitly state how many output channels do we want out of the convolution. And this number of output channels are trained during the optimization procedure. So the size of the output is defined by the tensor batch size times output channels times H out times W out, and size of the input is batch size times input number of channels times H times W. And for every output channel, we compute the procedure defined by the formula. So there is a bias term, and there are weights that apply to the input batch, and so thus we compute a dot product for all possible positions of the filter. So a number of learnable parameters can be defined by the following formula: number of channels at the output, number times brackets number of channels at the input times size of the kernel plus 1. And more detail you can find it at the link below, how the definition of the layer is performed in PyTorch. So a few considerations about choice of the size of the image. So one of the consideration is that we have to pick an odd number per dimension for kernel, so we could have the center accessible. And in case of large images, we may start with a larger kernel sizes, or use some kind of dilations to reduce the size quicker. And then we can work with a regular 3x3 kernels. Or if size of the image is not that small, we just may start with kernels 3x3. And we have to keep in mind how the receptive field, which is the area of the original feature map that is convolved or contribute to the pixels of the higher level output feature map. So if in case we have original feature 5 by 5, and then we have first convolution 3 by 3. It convolves to a single pixel, and then on top of it we can have a second convolution, and it actually produces just a single pixel, and this single pixel actually captures information from the original area 5 by 5. And by stacking several convolutions, we can add more and more information about the raw pixels to the higher order maps. It looks like a good idea. However, it doesn't grow that fast. So just as a exercise, you may answer the following question: how many 3 by 3 convolutions should we use to recognize image of a kid of the size 100 by 100? And it turns out that it should be around 50, and which is not very well, not too much, but I think we can make it lower by I think we can make this depth smaller by applying special techniques, which is called pooling. It is actually another type of layer that is a basic building block inside PyTorch, and it effectively averages or maximizes input features that are located inside the square or filter size of certain dimensions. So it can reduce the layer size by a specific factor. Like here we have 4 by 4, which is 16, that turns into 2 by 2 after max pooling operation. And max pooling here is that instead of averaging, we use a max function. And you can think of different kind of aggregations there, but maximum and average are the most popular. And also this technique makes neural network less sensitive to small image shifts, because it would not matter if our original image has been located like here or located like here. In the end, you would just say that our image is located across those 4 pixels, and this we information about this we get without any additional parameters that we have to train during the optimization of the neural network. So let's have a quick look how pooling works. So again we are looking at the image from the camera, and we can apply pooling size 2 or 3. It effectively reduces original image by factor 2 by 2 by 3 by 3. So it is quadratic reduction, and you can play with different aggregation function, or either maximum, which makes the image very similar, or averaging. But I hope it's clear now. So here is a quick self-check. So please answer those questions for yourself. And important thing that we can combine a more complicated neural networks by stacking convolutional layers together. So here is a example of a building block that comprises a much more complicated neural network, and it takes the previous layer and then applies convolutions 1 by 1, 3 by 3, 3 by 3, and 5 by 5. And output of this neural cell, is passed to a downstream task. So out of those building blocks, we can construct a much more complicated neural networks. And this example of the state-of-the-art, it is called GoogleNet, or it was state-of-the-art some time ago. Since then, we have various others, but nevertheless, you may appreciate the size of this guy. Here you see the repeating blocks of the kind that I has shown on the previous slide. And if you check what would be activation of every layer, 3A, 4E, 5B, etc. So you see that you go from more abstract representation to something that looks a more and more higher level representation. So it was trained to recognize different kind of images, and you see those images somehow emerge on a higher level activations. The possible problems that we may encounter with large size neural networks, either related to memory errors like running out of memory, gradients can vanish or explode, the same is for activations, and popular solutions, either we can rely on the normalization technique we described at the previous module, or we can use the pre-trained networks. So pre-trained network is something that we pick from the library or wherever it is. In this example, we take an architecture that is called ResNet, and then we freeze all weights by setting requires grad to false, and then we add a layer to this neural network, to this model, or we substitute it with our own layer. So it is a final layer that we want to update during the training, and then we can optimize this model that would change parameters on a single layer. It makes training much more faster. And it was the basic alphabet that allows to combine image-aware neural networks, and it allows to deal with problems like image tagging, image captioning, image retrieval, morphing, encoding, or upscaling, or segmentation. It can work with not only images, but with point clouds. Just you have to somehow modify the dimensionality to match the features that we get from these kind of objects. In high-energy physics examples, convolutional layers can be applied to jet tagging, tracking of particles, to analysis of images of colorimeter, or analysis of the Cherenkov detector images. And there are many papers that describe how this can be done in particular. So there are libraries that you might be interested in that allow to deal with image related tasks, because it has been developing quite extensively for many years, and some tasks like data augmentation and maybe data preparation can be performed by libraries somewhere from somewhere else. So we come to conclusion, and important things are that images are the first-class citizens in deep learning world. Although they are high-dimensional objects and they demand for powerful techniques to be efficiently processed, There are adequate tools or building blocks, namely convolutions and pooling, which are integral part of PyTorch to address those challenges. And another great source of inspiration could be a pre-trained models that you can download from libraries like Torch Vision. It is a package that you can install by just running a single command. If you're interested, you can explore more additional information on this, and see you during the next episode of this lecture.